Assalamu alaikum. Welcome to the next lecture. In this lecture, we'll be discussing about uh, the fixed capacitor thermistor control reactor, that is FCTCR. So, in this SVC, we have some fixed capacitors which are also connected across the TCR. So, as I have told you in the definition of the SVC, we have uh, TCR and we might have some capacitors that are also provided to provide the reactive power in case of voltage is reduced. So usually you'll see that this TCR is never used alone. The capacitor is used and connected in parallel with this TCR. It may be either mechanically switched capacitor, that is MSC, or thyristor switched capacitor. So mechanically switched capacitor, we might be using some sort of mechanical switch like circuit breaker, and thyristor switched capacitor we will be using the thyristors. The TCR provides a continuous controllable reactive power only in the lagging power factor. As you can see this diagram, as I have discussed it earlier, that from this point to this point we have the control of the voltage, and this is on the lagging reactive power. We are only drawing uh, this reactive current, inductive reactive current by this TCR. There is no control in the we can say leading power factor range. It is because we are assuming only the voltage is more as compared to the nominal voltage. In that case, we will be using this. If this voltage is less, so we cannot use this for that case. So to extend the dynamic controllable range to the leading power factor domain, a fixed capacitor bank is connected in shunt with the TCR. So if we want to increase the controllable range in the leading power factor domain, we have to use the capacitors as well. The TCRMV is rated larger than the fixed capacitor to compensate or to cancel the capacitor MVA and provide the net inductive reactive power, a lagging power factor operation which should be desired. For example, we want that the rating of this, that means the current that is drawn by the TCR should be more than the current at alpha is equal to 90 degrees with respect to peak. The current drawn by the TCR will be maximum. That maximum current should be more than the current drawn by the fixed capacitor. It is because when that is more than the current drawn by the fixed capacitor, the total current drawn by these two components which are parallel, that is equal to this current plus this current. Overall we can consider them only one capacitor. There may be one or two or three depending upon the need. So we can assume them, club them in one capacitor. So we assume that the current drawn by the capacitor is IC and this is IL. So this IL at the we can say protection limit at alpha is equal to 90 degrees with respect to peak. This should be more as compared to this, so that the total current when we add them, because this the total current, since they are reactive current, will be equal to this current minus this current. It should be reactive. It should be inductive reactive. That means it should be lagging in nature. That's why the rating of this TCR should be more as compared to the capacitor. The fixed capacitor banks usually connected in star configuration are split into more than one three-phase group. So we can connect them, not the whole capacitor in a one single three-phase group. We can connect them as small, more than one three-phase groups. Now let us discuss about the operating characteristics of FC TCR, that is the fixed capacitor thermistor control reactor. We'll first discuss it without the step-down transformer. The fixed capacitor extends the operating control range of the SVC to the leading side as compared to the shown earlier. Because this was only from this point to this point, it is only on the lagging side. The leading side, the leading side only from this point to this point. So actually, this is the ISVC current. ISVC current will be equal to IL current minus IC current. When IC is more as compared to IL current, you will see ISVC will be in the negative direction. That's why it is showing will be having the control range in this leading power factor or leading current range. The ISVC current can be expressed as a function of system voltage V and a compensator susceptance PSVC as follows. So here we will not be using the values of the current, we will be using directly the value of the susceptance and the voltage. So that is one and the same thing. So in that case, when this is the case, ISVC is equal to V into J BSVC, where uh, taking care of J here. So BSVC, then BSVC is equal to BC plus BTCR. You can see from here, it's from here. BSVC is equal to BC plus BTCR. Since the value of this is fixed, the total uh, reactance susceptance of this TCR will be BTCR, and this BL will be fixed when this is when alpha is equal to 90 degree with respect to peak, or 0 degree, sorry, when alpha is equal to 90 degree with respect to origin and 0 degree with respect to the peak of the input voltage. Here again, this BSVC is equal to BC plus BTCR and BC is equal to omega C, where BTCR is equal to minus BL. We have to take care of that minus as well because BTCR will be negative. Now, as I have told you that this capacitor is used only when the voltage is less than the reference voltage. And this capacitor is fixed, it will act as a simple reactance. When voltage increases, this current will increase. The current through the capacitor will increase, because in that case, when voltage is less as compared to the nominal voltage, will not be using this BL, because it will further reduce the voltage beyond that voltage which is already less than the reference voltage. So that is why, for example, if the system voltage is this much, the current drawn by this capacitor will be this much, and there will be no control, there will be not will not be issuing any alpha or firing out to this. We'll keep it off, so it will act like a reactance. As I told you earlier, when we discuss different resistors of different value, their operating characteristics will be like this, like this, like this, depending upon the value of resistance. Since voltage and current was considered to be positive in that case, so it was the VI characteristics of the resistors, or even for TCR, will be in the first quadrant. But here the VI characteristic for this BC will be on the second quadrant, because we are assuming this the current that is drawn by the BC will be negative of the current that is drawn by the BL. That's why it is drawn on the second quadrant. It will draw the current which is negative of the current drawn by the TCR. So from this point to this point, if voltage increases from 0 to this, the current increases from this point to this point for this BC, and at this point the value of the voltage will be the reference voltage. Now this line is known as protection limit, and actually this point should be known as protection limit, or for when we have this range, this will be always the protection limit, because whatever be the voltage, this it will produce the reactive power as per the voltage, and this will be the current at this point, and we can say this is a protection limit at that voltage. So for all these line, you will see that BSVC is equal to BC, because BTCR will be 0 for this case, since we're not showing any firing into this. Alpha will be equal to 180 degrees. It is not actually connected to the system. Now at this point, if the system voltage increases further, now if we will not issue any firing to this, you'll see voltage will go on increasing. Voltage will go on increasing, current will increase. In that case, as I have shown you for this case, if the voltage increases, we'll issue firing pulse to this as per the desired value. So the voltage will come from this point to this point, and A1 will be the operating point. For similarly, if voltage increase like this, we'll issue some uh, firing to this. It will consume the reactive power, and it will make this system voltage to come, let us say, at this point. Similarly, if the voltage increases further, we can decrease the value of alpha for this TCR, and it will, let us say, increase, or it will operate at point this. If the voltage increases further, we issue again the value of this. We can say we decrease the value of alpha for this TCR. It may reach to this point, At this point, you can see the value of current for that is drawing by this, and the value of current that is drawing by this is same at this point. So you will see the control range for us will be only in the capacitor range, because from this point to this point, even if we are supplying alpha to this TCR, the total current that is drawn by this and this will be capacitive in nature, because the current drawn by BC will be greater than this, but at this point it will be equal. So what I mean to say is that when this is less than this, when the current drawn by this is less than this current drawn by this capacitor, you will see ISVC will be capacitive in nature. If the rating of these two would have been same, we will always be in the capacitor range. Since, as I have told you, we have to keep this rating more than this rating, so the current drawn by this at alpha is equal to 90 degree will be greater than this, that is at here. So we have increased the range in inductive range as well. So when system voltage increase further, we can issue alpha, uh, we can decrease alpha beyond the earlier value, which makes this current equal to 0. So it may reach to this point, like we have already discussed for A1, A2 and this, and then it goes on, and this is the point we can say absorption rate at alpha is equal to 90 degree, which makes this inductance fixed. And as I told you, if this alpha increases, we don't have control after that, so this voltage current characters will increase like this, as that has increased like this. After that we may have current limit, but this is how this has been explained. This is the protection limit, this is the control range, this is the absorption limit at alpha is equal to 90 degree. At this is BSVC is equal to BC plus BL. Here BSVC is equal to BL. This is the capacitor range, this is the inductor range, this is the total control range. This is for the overload case. Now, susceptance characteristics should be this. As already we had told, the susceptance characteristics was like this in case of single TCR, but here BSVC is equal to this BC plus BTCR, and BTCR is negative. Now you can compare this equation. Y is equal to mx plus c. This is a constant term, this is a variable term. Here m is -1, that is minus slope, and c is the y-intercept, that is BC, and this is the variable, that is total y. So when you draw the line for this, it will be a line that is passing through y-axis, and it is cutting y-axis at BC, because this will be the y-intercept. Y is equal to mx plus c. This will be y-intercept. That is what you will find over here. You can give the value, and you can also find it out by giving some values to this. When alpha is equal to 180 degrees with respect to origin, or 90 degree with respect to peak, this BTCR will be equal to 0. BTCR will be equal to 0, then BSVC is equal to this BC, that is like this at this point, and this will be positive, because this is positive, this is negative. When when BTCR, that is when alpha is equal to 90 degree with respect to the peak, and 180 degree with respect to, when alpha is equal to 0 degree with respect to peak and 90 degree with respect to the origin, this BTCR is equal to minus BL. So total BSVC will be equal to BC minus BL. It has shown here plus BL, it should be minus BL. So it will be equal to BC minus BL. So the total curve will be like this, and there will be some point when this BTCR will be equal to this BL, but since it's negative, so BSVC will be equal to 0, and you will see that this BSVC will at that point will be equal to 0. So this will be the curve of the BSVC, modified curve of BSVC, as compared to this for a fixed capacitor TCR. Now these two operating characteristics show the susceptance, show the operating, that is VI characteristics, and the susceptance of this type of compensator respectively, and both also show a VR protection as well as VR absorption. This is the protection limit of the FCTCR. This is the absorption limit of the this FCTSR. Similarly, this is the absorption limit, this is the protection limit. By dimensioning or changing the reactance of capacitance, or this capacitance of this fixed capacitor, and reactance of the TCR, the protection and absorption range can be selected or changed accordingly as per the system requirement. Now let us discuss the same with a step down transformer. Let us say we have a transformer whose susceptance is given as B sigma. The compensated susceptance BSVC can be given by the total compensated susceptance will be B sigma into BC plus BTCR divided by B sigma plus BC plus BTCR. So as you can see, in case of reactances, if the two reactances are in series and then the series combination is parallel to the third, we do the same thing. Here you can see we have two parallel, usually parallel are this parallel susceptances or parallel admittances are added, and series are calculated the way we calculated the parallel combination of reactances. Same is the case here. So we add first this parallel susceptance and then calculate the overall with series the way we do it for the parallel resistor. So it will be equal to B sigma into BC plus BTCR over B sigma plus BC plus BTCR. Let us divide it by this B sigma. It will be equal to BC plus BTCR, that is this. This will be B sigma. B sigma is equal to 1. This will be BC plus BTCR divided by B sigma. So B sigma is the susceptance of a transformer and BTCR is variable from 0 to BL. When firing angle is 180 degree, it will be equal to 0. When firing angle 90 degree, it will be equal to BL. And this firing angle are measured with respect to the origin of the input voltage. From this equation, the susceptance limits can be calculated. Susceptance at the protection, that's capacitor limit at BTC when BTCR is equal to 0 will be simply equal to BC B sigma divided by BC plus B sigma. When BTCR is equal to 0, it will be equal to B sigma into BC divided by B sigma plus BC. When BTCR is equal to BL, it will be equal to this B sigma into BC plus BL divided by B sigma plus BC plus BL. And you have to take care, I have not consumed that minus into BL because we are assuming that BL is negative. That's why it has here also shown this B sigma plus BL. The negative has been consumed with BL. We are assuming this, where this making the mind that BL is always negative. This is the protection limit. We can say this is the absorption limit. Where we can assume what will be the value of BSVC, and in this case this will have the maximum value. In this case it will have a minimum value. It must be noted that BL is a negative quantity. That is what I was just telling you. An analysis of the equation shows that the total susceptance of BSVC, total susceptance BSVC of the static or composite does not change linearly with BTCR because BTCR is in, you can see from here, BTCR is in numerator as well as in denominator. So there is not a linear relation. However, if BC by B sigma is very small as compared to 1, and BL by B sigma is very small as compared to 1, which is usually the case, the non-linearity is relatively very small. We can assume a linear relation. This assumption implies that the reactance of the coupling transformer is greatly smaller than the reactance of the either the fixed capacitor or TCR. So that means the reactance of the coupling transformer will be smaller as compared to the reactance of the capacitor and the reactance of the TCR. BSVC equations can be approximated by the linear relation as follows. So this is the earlier relation. Now I will take it to the numerator. The whole term to the numerator, it will be equal to 1 plus BC plus BTCR raised to power minus 1. So when I open it by using the binomial theorem, it will be equal to 1 minus BC plus BTCR by B sigma into BC plus BTCR. It will be definitely having a higher order term since B sigma is greater than these two terms. You will see that will be neglected when it is a square term. So the total term will be 1 plus BC plus BTCR divided, sorry, 1 minus BC plus BTCR divided B sigma into BC plus BTCR. When you open it up, it will be equal to 1 plus BC by B sigma into BC plus 1 minus twice BC plus BL divided by B sigma into BCR. This will be the linear relation of this FCTCR with coupling transformer. You can see when BTCR is 0, this will be only this much. When BTCR is equal to BL, we have this much of value present. So in that case we can calculate it. This will vary linearly. The susceptance limit based on the above linear equation are. So BSVC max will be equal to when BTCR is 0. and BTCR is 0, so it will be equal to 1 plus 1 minus BC divided by B sigma into BC, that is this, and BTCR is BL, it will be equal to 1 minus BC plus BL divided by B sigma into BC plus BL. This will be BSPC minimum. So in that case, we'll be assuming this to be linear, and we'll calculate the production as well as this absorption limit. Now we can also calculate the value of the transformer secondary voltage. That will be equal to V2, that is here. That is V2 is the voltage across TCR and this fixed capacitor. It will be equal to ISVC divided by J into BC plus BTCR. So V2 will be equal to current divided by susceptance. So that's what this relation comes from. So the ISVC can be expressed as a function of the system voltage V and the total compensated susceptance. Note that the secondary voltage is in phase with the system voltage because of the transformer. So V2, when we use the voltage divider rule, we calculate V2 is equal to the reactance, which is across which we are calculating the voltage divided by the total reactance of the total resistance of the system. But here, since we are dealing in terms of the susceptances, so in that case we have to take the numerator will be having its susceptance of the element across which voltage is not measured. So it will be equal to B sigma divided by B sigma plus BC plus BTCR, that is this combination. So at the operating limits of the compensator, so V capacitor, that means when alpha is equal to 90 degree with respect to the peak and 180 degree with respect to 0, in that case BTCR will be equal to 0. This will be equal to B sigma divided by B sigma plus BC because it will be 0. And then when we divide this by B sigma, it will be equal to 1 divided by 1 plus BC by B sigma. And then when you take it to the numerator, it will be equal to 1 plus BC by B sigma whole raised power minus 1. And when you open it up by the binomial theorem, it will be equal to 1 minus BC by B sigma. Similarly, for this case, you divide by first B sigma and alpha is equal to 90 degree with this, 90 degree with respect to origin and 0 degree with respect to peak. In that case, BTCR will be equal to BL. So when you divide by B sigma, it will be equal to 1 divided by 1 plus BC plus BL divided by B sigma, and when you take it to the numerator and open it with binomial term and neglect the higher order term, it will be equal to 1 minus BC plus BL divided by B sigma. This is the voltage at two extremes of the TCR, that alpha is equal to 0 and alpha is equal to 90 degree with respect to peak. Now let us discuss about, or we can say, let us have a comparison between the mechanically switched capacitor and thyristor switch capacitor. So actually, since we are using the FCTCR, we can use a mechanical switch capacitor or thyristor switch capacitor. So we will having the comparison of these two. So in certain applications, especially those involving few capacitor switching, when we do the open and close of this switches very rarely, so we can use a mechanical switch capacitor because it offers acceptable performance at much lower compensating system cost than TSC and TSR, because if you use TSC, it will be costlier as compared to mechanical switch capacitor. One more advantage of MCTCR scheme lies in its lower capital cost, as I have told you here. From the elimination of the thyristor switch, because we will not be using the thyristor switch, which will be very costly in the capacitor. Another advantage is the reduced operating cost in terms of losses. There will be less loss because switching loss will not be there in case of this MC, that is mechanically switched capacitor, or we can say MSCs. And usually this mechanically switched capacitor, as I have told you, it may be mechanical switch, which may be a circuit breaker, and thyristor switch will be thyristors. And we know that the switching losses for thyristors are more as compared to the mechanical switch. That's why while using the mechanical switch capacitor, we'll be having less losses. The disadvantage of this is a lower speed. That is, mechanically switched TCR is the lower floor speed of the response. Some studies shows that to compensate for the lower speed and to achieve the level of transient stability similar to that of the thyristor switch capacitor, thyristor controlled capacitor at 25% higher rated MSC TCR SVC may be needed. That means for when we use a mechanical switch capacitor, we have to use 25% higher rated this type of MCV, sorry SVC, which uses the MSC. In that case, we might have the similar level of the transient stability, because uh, we are finally we are discussing about the voltage control, and voltage control has a direct impact on the transient stability, because transient stability also depends upon the voltage of the system. If voltage of the system remains its value, because during the fall this voltage goes very down, when we increase the voltage, this transient stability will increase, because area under the curve, that is P delta curve, will increase. The mechanical switch can close in 2 cycles and open in about 8 cycles. That's very huge amount of time compared to one cycle with thyristor. That is, 1/2 cycle it will be closed and 1 cycle it will be open. So this is the disadvantage of the mechanical switch. It takes time to get on, and it takes time to be put off. Another problem with the MCTCR relates to the trapped charge that is invariably left on the capacitor following deionization. When we open the switch, that's mechanical switch, it results in the trapped charge that is left on the capacitor. So that is actually a danger. So the residual charge on the capacitor is usually dissipated in about 5 minutes through discharge resistors built into the capacitor units. But this is again a long time to discharge, because sometimes you may require the capacitor before this 5 times. So in that case, it is very difficult. So this is also a disadvantage. If the capacitor is switched on within 5 minutes after deionization, that is what I have told you, the trap charge may be lead to increase in switching transient. In that case, switching transient may take place and transient stability may be upgraded. The mechanical switch or MSC, the mechanical switch capacitors can be switched in only when capacitor is discharged. So that's very important point. One solution to this problem of trap charge is to connect a small magnetic transformer, such as potential transformer, in parallel with each phase of the capacitor bank, and it will dissipate the trapped charge within 0.15 seconds. So in that case, this will help a great extent. The TCR in MSC TCR is designed to have the lower inductance as compared to the TCR in TSC TCR SVC of similar rating. So the inductance of this TCR, which is used in MSC TCR, is lower as compared to this. This design is to permit the increase of the overall capacity of transient balance and capacitive reactive power output. Because as I have told you, the rating of this type of this SVC should be 25% more, and it is done by keeping this TCR or the reactance of this TCR lower as compared to this. A lower inductance in TCR produces an increased level of harmonics. So in that case, this is another disadvantage, and it is more elaborate filtering than TSC TCR. So this is one more disadvantage. Now, the mechanical switch also possesses a finite life, typically 2000 to 5000 operations. So because of their wear and tear, there is only up to 2005 times 5000 operations. So they possess the finite life as compared to the infinite life and infinite switching of the thyristors. The mechanically switched capacitors are usually switched 2 or 4 times a day. They are connected during heavy load condition and removed under the light load conditions. So usually they are not frequently switched on and off. We can put them off during the light load condition, because light load condition we may have a good amount of voltage, and during the heavy load conditions, the voltage is low, so we have to connect them. So we know that they are used in off-peak period, because in off-peak period usually day has 2 off-peak periods and 1 peak period, so we can use them accordingly. So the losses of the mechanically switched capacitor are fairly low, and they lie in the range of 0.02 to 0.05% actually of the total rating of the capacitors. So this is about the fixed capacitor TCR, whether we are using the mechanically switched capacitors or we are using the thyristor switch capacitor. I think today it is enough. Thank you.